In this lesson, we'll create our first application. I'm going to show you how to create a new project in a new VI. Start with the Getting Started window. Now I'm going to show you how to create a new project in a new VI. Start with the Getting Started window and click Create Project. Choose a blank project and click the Finish button. First, I'm going to save my project. I'll save it to my desktop and call it Simple VI. Notice LabVIEW creates a Simple VI project file. Now let's create a new VI. You can create a VI in LabVIEW in a couple of ways. From within a project, right-click My Computer and select New VI. Or, with the project open, select New VI from the File menu. You should name VI something useful, so I'll rename it as Straight Line Equation and save it. Now I see my new VI in the Project Explorer window. And if you look at the files, you see a project file and a VI file. Let's develop the front panel, which is our user interface. This is where we find controls and indicators for our interface. Notice the different palettes: numeric, Boolean, string. In this case, I need a numeric control. I select that, place it on the front panel, and rename it. Next, I'll place another numeric control and call it X. If you already know what control or indicator you're looking for, you can click Search and type in the name. In this case, I'm looking for numeric control. I can find it right here. I'm going to place this and rename it B for the y-intercept of our straight line equation. I can align these controls this way, and then I'm going to put a numeric indicator down for my output, y. Now let's create the code. First, switch to the block diagram. This is where all the code and logic goes. Notice that all of my controls and indicators show up as terminals on the block diagram. You can rearrange them as it makes sense. In this case, my equation is mx plus b equals y. To find required nodes and functions, right-click the block diagram, or select View Functions palette. There are different palettes here to define your code. In this case, I'm looking for the multiply, which is under the Programming palette and under Numeric. Here we see the multiply function. I'll place it on the block diagram. Now I'm going to wire the slope by clicking here and then clicking the input of the multiply to connect them. Now I need an add function. Since I know the name, I can go to the search and type add. I'll place it here and click the output of the multiply and the input of the add function to connect them. For B, I'm going to click multiple times and wire this up. If you want to clean up this wire, you can right-click the wire and select Clean Up Wire. Finally, I'm going to wire the output of the add function to the Y indicator. Let's enter some values and run this VI. When you develop a VI, the position of your mouse cursor on objects in the window determines which tool is active. For example, to operate on a control, like changing a button value, you want to move the mouse cursor near the middle of the control until the mouse cursor appears. When you click, you can operate on the control. To change text, move your mouse cursor over the text until the text cursor appears. Now when you click, you can modify the text. To move a control, move your mouse cursor near the border of the control until the Move cursor appears. Then you can drag the control to move it. To resize a control, move your mouse cursor over any of the small blue resizing squares until the Resize cursor appears. Then you can click and drag to resize the control. To wire objects on the diagram, move your cursor near an input or output until the Wiring cursor appears. Practice resizing, moving, selecting objects, and wiring. Let's look at some wiring tips. If you need to select a wire, you can click the section of wire you need. If you keep clicking the wire, you can select more wire sections connected to it. Click any empty space to deselect the wire. When developing a VI, you sometimes end up with broken wires. You can either remove each broken wire by selecting it and pressing Delete, or you can press Ctrl-B to remove all broken wires. Note that using Ctrl-B to remove broken wires removes broken wires that you don't see, as well as those you do see. For example, it will also remove off-screen wires or wires in other event cases. If you want to clean up a single wire, you can right-click the wire and select Clean Up Wire, or just press Ctrl-U. If you want to clean up a section of code, you can select the section and click the Cleanup button on the toolbar. If you want LabVIEW to try to clean up the entire diagram, make sure nothing is selected and then click the Cleanup button on the toolbar. Let's look at different ways to search for controls and indicators. You can browse the palettes for available controls and nodes. If you know the name of the controller indicator, press Control Space and search for it. For example, type Add. Then you can double-click to place the add function. You can also click this search button to search for controls or functions by name. From the search results, you can double-click an item to view the palette that contains it. This is helpful if you would like to see related items and palettes. Lastly, you can search for an item here in the global search box. This does a global search, which returns results from menus, toolbars, the online manuals, as well as palette items. Let's talk about how to make your code more readable, both to yourself and other developers. You can make your code more readable by labeling constants to specify their purpose. For example, I can select these string constants and make their labels visible, and then enter the labels exceeded message and normal message to make the purpose of the constants more clear. You can also label wires by right-clicking them, selecting Visible Items, Label, and typing text. You can create comments on the block diagram by double-clicking the empty space and typing. You can use comments to document the logic of your code. Let's switch to the front panel. In the same way, you can create free-floating text on your front panel, which can provide information to your user. Use Boolean controls, indicators, and constants to enter and display Boolean or true-false values. To place a Boolean control, open the Controls palette, extend the Boolean palette, and choose one of the Boolean buttons. You can switch a Boolean to either a control or indicator by right-clicking and selecting Change to Indicator or Change to Control. For this Boolean, I can also modify the text on the button. Right-click the control again and notice the Mechanical Action setting. This important setting determines how the Boolean control behaves. Let's take a closer look at the two most common mechanical action settings. First, let's examine the latch when released mechanical action behavior. Latch means that if you click the Boolean control, it will change value and reset back to its default value. This LED indicates when LabVIEW has read the value of the Boolean control. When released means that the Boolean control will register a click only if you click and release your mouse button while the cursor is on the Boolean control. If you click and hold your mouse button on the control and then move your cursor off the control before releasing the mouse button, then the control will not register the click. This is a way for a user to cancel their mouse click and is the behavior of most software applications. When I do this, notice that the LED does not turn on because I am releasing my mouse button when my cursor is off the control. Latch behavior is common for items like OK buttons and stop buttons. Now let's examine the switch when released mechanical action behavior. The when released part acts the same, but the switch part is different. Switch means that if you click the Boolean control, it will change its value and stay at the changed value. Switch behavior is common for things like a Boolean toggle setting or a power button. Here we see some common examples of Boolean controls and indicators. Use Boolean controls when you want the user to specify whether to log data to a file, choose between serial and GPIB communication, turn the power off or on, or click a button. Boolean indicators are often used to signal when a threshold has been exceeded, or to indicate when a digital line is high or low. Use a numeric data type when the user needs to specify how many samples to read from an acquisition hardware, and the application must display the measurement result. You use numeric constants on the block diagram for mathematical constants or conversion factors. To ensure that your VI functions effectively and efficiently, it's important to select the appropriate format for your numeric data. In LabVIEW, we call these formats representations. LabVIEW represents numeric data as floating point numbers, fixed point numbers, integers, unsigned integers, and complex numbers. Numeric data types differ in two ways: the number of bits they use to store data and the data values they represent. To choose the representation of a numeric control, indicator, or constant, right-click the object, navigate to Representation, and choose the representation that best fits the range and precision requirements of your data. Before we examine each numeric representation, let's look at how LabVIEW stores data. The data type of the object affects how LabVIEW stores data for controls, indicators, wires, and other objects. For a numeric object, LabVIEW allocates an area of memory that is at least 8 bits wide. Depending on the required range and precision of the data object, the area of memory that is allocated can range from 8 bits to 128 bits wide. Certain bits in this memory allocation are defined by LabVIEW to store specific elements that comprise the number, such as the fractional portion of the number and whether the number is positive or negative. An unsigned integer is any whole number greater than or equal to 0. In LabVIEW, unsigned integers may be 8, 16, 32, or 64 bits wide. The bit width provides the required range of possible numeric values. Click each numeric representation to learn more about it. Signed integers are similar to unsigned integers, except that they can be positive or negative. The most significant bit determines the sign of the number. Because of this, the absolute range of a signed integer is half of that of its unsigned counterpart, but the total range is just as wide. Fractional numbers are represented by multiple floating point formats. Floating point numbers have a very broad range and degree of precision. Double precision is the default format for numeric objects. For most situations, use double precision floating point numbers. Use single precision floating point numbers when memory savings are important, and you will not overflow the range of numbers. Signed and unsigned integers and floating. In addition to signed and unsigned integers and floating point numbers, LabVIEW also supports fixed point and complex numbers. For more information on these formats, refer to the LabVIEW help. It's possible in LabVIEW to wire an object of one numeric representation to an object of another representation. LabVIEW automatically converts from one data format to another. This is called coercion. LabVIEW coerces to the data type that does not result in fractional data loss. In this example, when adding a double precision floating point numeric to a long integer, LabVIEW coerces the long integer to a double precision floating point numeric, and then adds the two values together. If both data types are integers, LabVIEW coerces the data type with a lower maximum value to the data type with a higher maximum value. In this example, LabVIEW coerces the signed integer to an unsigned integer. Because LabVIEW attempts to coerce a negative value to a data type that does not support negative values, the function generates a value of 6,531 instead of -5. LabVIEW places a coercion dot on the block diagram to alert you that the value passed into the node has been coerced to a different representation. In certain coercions, coercion dots may lead to an increase in memory usage and execution time, and a decrease in accuracy. In the case of the previous example, Coercion resulted in very inaccurate data that could impact the effectiveness of your application. To eliminate coercion dots, match the output data type of the control or constant to the data type of the receiving terminal. However, sometimes it's not possible to select matching representations for objects and terminals. In those cases, the best solution is to use numeric conversion functions. Right-click the wire and navigate to Insert, Numeric Palette, Conversion, and then select the appropriate function. Repeat this for the second wire and change the representation of the indicator. Examples of using the string data type. Use a string control to allow the user to input their username. Use a string indicator to display the status string to the user. You can also use string constants on the block diagram. To place a string control or indicator, open the Controls palette and expand this category. Place a string control on the front panel and enter the text you want. Right-click the string and open the Properties dialog box. You can change the string display style. You can activate such options like Limit to a single line, Wrap at word breaks, Update value while typing, Show vertical, horizontal scroll bars, and Size to text. You can also right-click the string control and change it to an indicator. On the front panel, an enum appears as a predefined list of items that the user can select. On the block diagram, the enum represents the selected item as an integer. In this example, voltage is represented as a 0 on the block diagram, and temperature is represented as 1. Using an enum is useful if you would like to limit the user to only predefined items to choose. To place an enum control or indicator, open the Controls palette. Go to this palette and select Enum. Right-click it and select the Edit Items command to define your enum items. Enter the items in the Enum Properties dialog box. Notice that each item has a corresponding value. On the block diagram, the enum terminal is blue, which indicates that it outputs an integer value. You can choose different visual styles for a control or indicator by using different styles from the Controls palette. Right-click the front panel to explore different palettes. Here, you can choose a visual style for a control or indicator. To change the properties of multiple controls and indicators at the same time, select them all, right-click, and select Properties. Then select the properties you want to have, such as a visible label or an enabled state. Use the Dac Assistant Express VI to get started with acquiring data from NI-DAC in a VI. The Dac Assistant Express VI is good for finite sample acquisition or generation. Starting with a new project, right-click My Computer and navigate to New VI. To get started with acquiring data from an NI-DAC device in a VI, first create a DACMX task and then use the DAC task in your VI. Starting from a new project, I'll create an analog input DAC. Use the Dac Assistant Express VI to get started with acquiring data from NI-DAC in a VI. The Dac Assistant Express VI is good for finite sample acquisition or generation. Starting with a new project, right-click My Computer and navigate to New VI. Switch to the block diagram. Press Control Space and search for Dac Assistant. Place the Dac Assistant Express VI on the block diagram and wait for the configuration box to appear. Express VIs require minimal wiring because you configure them with dialog boxes. Select Acquire Signals, Analog Input, Voltage. Then from the Physical tab, select PCI 6221 and AI0 and click Finish. In the Dac Assistant dialog box, I'm going to set the acquisition mode to N samples, the samples to read to 1000, and the rate to 10,000, and click OK. The building process takes a moment to finish. Right-click the data output of the Dac Assistant and create a graph indicator. The Dac Assistant outputs a dynamic data type. Expand the Dac Assistant to show the error out terminal, then right-click it and create an indicator. Switch to the front panel. And now I'll run the VI and acquire data from hardware. Starting from a new project, I'll create an analog input DAC task. Right-click My Computer and navigate to New NI-DAC task. Now I'll configure it to acquire temperature data from a thermocouple. For this, I need to extend Acquire Signals, Analog Input, Temperature, and choose the thermocouple. Then from the Physical tab, I'm going to select PCI 6221 and AI0. Enter thermocouple as a task name and click Finish. In the Dac Assistant window, I can set the task configurations. For example, set the max signal input range to 50. Run to test the task and click the OK button. Now I'll create a VI where I'll access this DAC task and acquire data. Right-click My Computer and choose New VI. On the block diagram, I'll begin by placing a DAC start task. And I can right-click the task input and create a constant, and set the task constant to the thermocouple task I just created. The DAC start VI starts the acquisition. Then I'll place a DAC read with the following settings: analog, single channel, single sample, single floating point value. Now I'll create an indicator to show the single sample of acquired data. Next, I'll place a DAC clear task, which safely stops and clears the task and releases any resources. Next, I'll connect the task wires so that each node is operating on the same thermocouple task. Finally, I'll connect the error wires and create an error indicator on the error out output of the DAC clear task VI. Now let's run the VI and acquire data from hardware. This is an example of a VI that acquires, analyzes, and visualizes data. The Acquire section of code acquires data. This VI acquires a temperature from a thermocouple measurement task. This analysis code checks if the acquired temperature exceeds a maximum threshold and selects a corresponding string. This section visualizes data by displaying relevant data on indicators on the panel. You can also visualize data by logging it to a file. We'll discuss writing data to a file in a later lesson. Now I'll show you how to create a DAC VI using a DAC task that acquires multiple hardware time samples from a single channel. Notice that this project already contains an analog input voltage DAC task. Double-click it to open the Dac Assistant. Here we have N samples in the acquisition mode. 2,560 Hz as a sample rate means that this task is acquiring at a rate of 2,560 samples per second. Click OK. Now let's take a look at the VI code. We already have a DAC start and an AI voltage task constant. Next, I'll place down a DAC read VI, and I'll set it to analog, single channel, multiple samples, 1D dBl. Next, I'll right-click the number of samples per channel input and create a control. Then I'll place a graph indicator to show the multiple samples of acquired data. I'll place a DAC clear and connect the task wires so that each node is operating on the same analog input voltage task. Finally, I'll connect the error wires and create an error indicator on the error out output of the DAC clear task VI. Now I'll run the VI and acquire multiple samples of data from hardware, which are acquired at the sample rate of 2,560 Hz. When acquiring data from an NI DAC device, you can take the DAC task approach or the full DAC API approach. The full DAC API approach replaces the DAC task with DAC nodes. The DAC task approach is intended to help you get started. To help simplify your initial ease of use, the channel, timing, and triggering settings are all contained in the DAC task. The disadvantage of this approach is that in order for you to modify a channel, timing, or triggering setting, you must make that change in the DAC task. You cannot make those changes directly from your VI with this approach. On the other hand, if you use the full DAC API approach, you use DAC nodes on the diagram to configure channel, timing, and triggering settings. You no longer need a separate DAC task object. Instead, you can programmatically configure the settings in the VI. In this example, the user can configure settings such as the channel, measurement range, sample rate, and number of samples to read, all from controls on the VI front panel. As you get more comfortable programming in LabVIEW and need more flexibility, you should always use the DAC API. The DAC API programming flow starts with creating a DAC task, configuring the task, starting the task, reading or writing data, and finally clearing the task. To create the task, use the DAC Create Channel VI. To configure the task, you can use the DAC Timing VI to set the sample rate, and use a DAC Triggering VI to set up a trigger. And finally, you can use the DAC Property node to configure additional and advanced settings. The DAC Start, Read Write, and Clear VIs work the same as before. Here's an example of a VI that uses the DAC task approach. Notice that this VI is using the analog input voltage DAC task. I can change the number of samples in this VI, but if I want to change the channel, sample rate, or other settings, I need to open the DAC task to make those changes. In contrast, here is an example of a VI that uses the full DAC API approach. All the DAC configuration settings are accessible in the VI. Notice that I can change the channel and sample rate within the VI. The typical instrument driver API programming flow is to initialize the instrument, then configure the instrument, initiate or start the instrument, read or write instrument data, and finally close the instrument. Some instrument drivers require you to initiate the instrument and others do not. When acquiring data from an instrument, you should start from an existing instrument driver example VI, because the example VIs are intended to show you the recommended way of programming that instrument. This particular instrument driver example initializes the instrument, configures the instrument settings, reads a single point of data from the instrument, closes the instrument, and checks for errors. After starting from an instrument driver example VI, you can then add your own analyze code and visualize code. Here's a summary of what you've learned in this lesson.